Finally, we would like to prove the sorting lower bound. This is very similar to the permutation problem. In fact, the permutation problem can easily give us a lower bound for the sorting as well, because sorting, to be able to sort, I need to create the sorted permutation of the input items. So at least it is as difficult as the permutation problem. However, if the block size is too small, we would like to show that this branch is not possible. In other words, the sorting lower bound should only be this term. So in rare cases where capital N is smaller than this factor, I would like to show that you cannot sort in capital N IOs. This is very intuitive, because in the internal memory, when the block size is small, or block size is 1, and capital N equals small n, we know that you cannot sort in n time, that we need n log n time to sort in the comparison model. We'd like to have the same or similar proof in the IO model. Again, to be able to prove a lower bound, we need to have assumptions and the model of computation precisely stated. We assume that the input is stored in, again, small n blocks. We only allow comparison between different elements. Again, the elements are atomic. You cannot split them, you cannot encode them, or you cannot create them. You can only compare two different elements. The important part is that all the other information is free. And finally, to be able to compare the elements, they have to be inside the main memory. The number of comparisons that you do, again, we're not counting. We're only counting the number of IOs you do. This in particular means that you can compare all the elements inside the internal memory for free. To be able to simplify the lower bound, we actually help the algorithm a little bit. At the beginning of the algorithm, when the algorithm receives the input, we tell the algorithm the order of the elements inside each initial block. In other words, we allow the algorithm compare all the elements in blocks for free. This might seem like a big help, but it's not too much of a big help, because the algorithm could have figured this out by doing n over b IOs anyways. It could reach blocks one by one, and since comparing the elements inside the main memory is for free, it could compare the elements of a block inside the main memory for free and then write them back to the disk. So this does not change the problem much, but it makes the proof a bit simpler. Okay, so let's see what the algorithm could do. The algorithm could read and write a block. Let's see what happens when the algorithm reads a block. Assume this block is being read by the algorithm. We know that this block is in the sorted order, or in other words, the algorithm knows the sorted order of this block. We know this because we have helped the algorithm to figure this out initially. Okay. So the algorithm knows the sorted order of these elements. The algorithm also knows the sorted order of the elements in the memory, because that's for free and it doesn't cost the algorithm anything. Okay. So I have a bunch of B sorted elements and I have a bunch of M sorted elements. How many different possibilities could be for the order of these elements? This has at most this many possibilities, because I need to only find the places of these B elements within these M elements. If the algorithm wants to write a block, that does not help at all with the comparison. So in other words, the algorithm does not gain any different information by writing blocks. So writing essentially does not help. And the important observation is that every time the algorithm writes a block, the order of the elements in the block are known. So we can always assume that all the blocks, for every block on the disk, the algorithm knows the order of the elements in that block. So it follows that after K reads, the algorithm can resolve this many possibilities. Observe that we need to resolve all possible states. The total number of different or sorted orders of the n elements is n factorial, but because we have ignored the order within each block, the algorithm just simply needs to resolve which state the sorted order of the element it belongs to. We observed from the previous lower bound that the number of different states is this much. So this is the total number of possible states of the final sorted order. Every time the algorithm does one comparison or one block read, it can reduce it by this much. This is how the number of possibilities are reduced. So therefore, it must follow that after this many, actually there's a typo here, so there should be a K there. Let me fix that. All right. So this is how many possibilities I can resolve after performing K reads. Obviously, this has to be the total number of states that I need to resolve. And now, using a math that is simpler than the previous math, it follows that K needs to be at least this much. So therefore, we obtain this lower bound for the permutation, for the sorting problem.